Welcome to Amplified Education, your exam prep friend. Today we are doing static friction. Please pause this video and try and answer these exam questions on your own. The question reads, Wade and Nadia investigate the static friction of three different surfaces, that is tar, gravel, and mud. Their goal is to determine the coefficient of static friction for each material. To do this, they attach a Newton spring scaled to a 5 kg box and exert varying forces at an angle of 15 degrees to the horizontal, as shown in the diagram. For each surface, they record the force required to make the box just begin to move. The following results are obtained. Question 1.1 says we must define friction due to a surface, and that is a force that opposes the motion of an object. And 1.2.1 says we must identify the independent variable. So the independent variable here would be the type of material that the box is placed on. In 1.2.2, it wants the independent variable, which would be the maximum static friction for each material. Then in 1.2.3, it is asking for the control variable, which should be the same box, right, with the same texture, same material of box, same mass of box. And that would be, again, the angle at which the force is applied. So that would be theta of force applied. Then in 1.3, the question says which material has the highest coefficient of static friction? So that would be gravel. And your reason in this particular for this particular question is that the static friction for the same object with the same normal force, FFS, is directly proportional to US. And so that obviously has to do with the roughness or the smoothness of the material. Gravel is particularly rough, and so there is more interlocking between the two materials that are in contact. And so that is why 1.3 would be gravel. 1.4 says explain why tar would require the smallest force to be applied before the object starts to move. Well, tar is smooth, right? Tar is smooth, and so if a tar is smooth, there is less interlocking between the two surfaces that are in contact, or the two surfaces that are interacting. 1.5, the angle of the force applied on the box is now decreased. How will that affect the coefficient of static friction? Right, increase, decrease, or no effect? So that would be no effect, because the coefficient of static friction depends on the two surfaces that are interacting, that are in contact. All right, it's a property of those particular two materials that are in contact, and so it would have no effect. It more has to do with the materials of the two surfaces that are in contact than any other thing. So that would be no effect, and so it would be a constant value for given materials. Then, if you look at 1.6, it says use the data provided in the table to plot a fully labeled graph showing the relationship between the applied force and the static friction for gravel road. Now, it particularly says you're showing the relationship between the applied force and the frictional force, not the static friction as such, right? But the friction, all right, the applied force and the friction for gravel road. So here I'm going to have friction on my y-axis measured in newtons, And here I'm going to have force applied measured in newtons. And then I'm going to have graph showing a relationship between the force that is applied and the frictional force, right? The frictional force. And then what I'm then going to do is that I'm going to come up with values I can use. I can see that the maximum value for the force that was applied there was 12 newtons, and I have 7 blocks going sideways. So I'm going to separate my blocks here. Maybe the difference between my blocks would be 2 units. So that is 0, 2, 4, 6, 8, 10, 12, 14. And I'm going to also go up in twos this way, but there are fewer blocks on the vertical axis. So I'm going to put my 2 here, my 4 there, my 6, my 8, 10, 12, 14, 16, 18, 20. That's quite a lot of points that are there. And so, but it's enough. It gives us a good graph, right? A wide range. If we had more values, then we would still use those points, right? So let's start plotting then. So if we then ask ourselves this, if we are only given applied force values on the x-axis, how are we going to get our friction values? And so remember, friction increases with applied force, particularly when we are looking at stationary objects. According to Newton's third law, for every action, there's an equal but opposite reaction. So if I apply a 1 Newton force on a stationary box and it does not move, it means the box is applying the same force towards me or in the opposite direction, and the same applies for friction as well. So if the force that is applied is 1 Newton and the object does not move, it means that the frictional force that is opposing that applied force then is also equal to 1 Newton. So let us now again begin. There's something else that you need to notice here, that the force that is applied is at an angle. So if you wanted to calculate the horizontal, right, the horizontal force, that would be parallel to the frictional force. Remember, friction is parallel to the surface. It's parallel to the surface the object is in contact with. And so if you wanted to calculate the horizontal force, all right, or the component of the horizontal force, then the component, of the applied force, then you'd multiply all of these values that are given in the table by cosine 15 degrees. So maybe let's put that disclaimer here that we are just going to plot the F applied at 15 degrees, all right, because that's the angle at which this particular force is applied. Okay, that's fine. We could work with that. And then we can now start plotting. Remember what I said earlier on, that if the force applied is 1, then the friction is also 1 as long as the object is stationary. And then if the force applied is 5, then the frictional force is also 5. Then if the force applied is 8, then the frictional force is also 8. And then if the force applied is 11, which is somewhere there, then the frictional force should be in between the 10 and the 12 there. Okay. Then the last one is 12. So that's where the force applied is. Okay, so those are your plotted values, and let's just connect those points. I'm going to start at, my graph is going to start at 0, even though there's no point like that is given on the table, simply because, remember, friction is a reactive force. So friction does not exist unless you start applying a force on the box. That's the first thing. But my graph is also not going to go beyond 12, because 12 represents the force that is applied just before the box starts moving, which in this particular case would be the maximum static friction, FFS max. And so this line that we've just drawn here, let's make the line maybe black so that we can clearly see it. Okay, this line that we have here represents static friction. Static friction, right? So this shows us that all of these forces were applied while the object was stationary. And these are all the varying values of static friction based on the force that was applied. And that's pretty much how your graph would look. Then the next question says, when the box starts moving, a constant horizontal force of 12 newtons is applied, right? Indicate this force on the graph. So to indicate this force on the graph, I could indicate that particular force anywhere above the maximum static friction, because remember, static friction is the maximum, it shows the maximum force that you need to apply for an object to start moving. And if we knew the value of kinetic friction, let's say we knew the kinetic friction to be 6 newtons or 4 newtons, all right? If the kinetic friction is 4 newtons for this specific material, then we'd have to plot a point there, right, going down from maximum static friction there, and then connect that, draw that in a straight line, because they said a constant force is applied. Now, this particular line that I've drawn here is showing us the value of FFK, the value of kinetic friction, because the object has now started moving. And so if the object has now started moving and I'm applying a constant force of 12 newtons, the kinetic friction will not increase with that force. The kinetic friction can't be 12. The value of your kinetic friction is always less than the value of your maximum static friction. This is showing you that you really need less force to keep an object moving than to cause it to move. Right, and that's pretty much what you would do there. And then what's the next question? The next question says calculate the coefficient of static friction for the muddy material. So to do that, first and foremost, you must not forget that the force that you're applying is acting at an angle. All right, so it is acting at an angle. So what I'm going to do is that I'm first going to draw a free body diagram showing all the forces that are acting on the box. All right, there's a normal force. Then there is force applied. Excuse my diagram, it doesn't, look straight. Force of gravity there. And then you have Fs. I would also advise you to represent, instead of representing the force that is applied, represent the components, the vertical and the horizontal component of the applied force. This will make your calculations a bit more easier. So maybe call that Fy and call that Fx. And then call this your friction, which is your FFS. And then this would be your Fg. All right. Then once you've done that, you will notice that these two forces, if the object continues to remain stationary, then these two forces are equal. That's very, very important. So first and foremost, to do this, you have to calculate the value of maximum static friction, but now using the horizontal component, particularly focusing on the muddy road. Okay. So you would say there that your Fs is equal to your Fx, which is equal to the force that is applied just to cause the object to start moving, multiply that by cosine theta, which is then equal to 10 cosine 15 degrees. And that would give you 9,66 newtons. Then remember, the formula for friction is given by FFS equals US Fn. Now you already have Fs, you've calculated here using the horizontal component of the applied force. You are looking for Us, but you do not have the normal force. Now, to calculate the normal force, you have to consider that there is a vertical force rather that is applied on the box. That is the vertical component of the applied force. That particular force provides a lifting effect which causes the box to be in less contact with the ground and causes the frictional force to basically decrease. So that upward pull as a result of that applied force at an angle is very important to be considered when calculating the normal force. Remember, a normal force is a support force, right? And so if there is a lifting Fy force as a result of the applied force at an angle, then the box is technically not entirely on the ground. And so the ground does not need to support the box more. And if friction is a contact force, then and there's less contact of the box on the ground, then friction should be less as a result of that force. And so it must be considered when calculating normal force, particularly because remember, normal force is directly proportional to the frictional force. So if normal force is affected by this vertical component, then it must be considered in the calculation of the coefficient of static friction. So to do that, we could add up all forces that are acting upwards, because vectors that act in the same direction must be added. So we could say Fn plus Fy is equal to Fg. Now we know that the mass of the box is 5 kg. We can multiply that by 9.8 and get 49. But to calculate Fy, we could say that 10 sine 15 degrees. So the normal force is equal to Fg minus Fy, which is equal to 49 minus 10 sine 15 degrees. Then we can just sub that in here. So remember, we already have FFS, which is 9.66, and we are looking for US. And then we can just sub in the 49 minus 10 sine 15 degrees. And then our US would be equal to 0.21. And that's pretty much how you would do that question. Hope that helps. Thank you.